primarily, are you aware? So primarily deciding about the architecture, whether it is dedicated है or time shared है या parallel है. So you got to decide about primarily the clock frequency and the sampling frequency. So usually your clock frequency divided by your sampling frequency at which you are getting the data would give you your budget, that in how many cycles should you complete the task. For example, if you are clocking a circuit at 500 megahertz, whereas your sampling rate is 1 megahertz, so you have 500 cycles to process it. Okay, so 500 cycles to process the design, and that basically a good design should not take just 5 cycles. Okay, आपके पास 500 cycles हैं to do so to say the acceleration जो आप पूछ रहे हो. So you have like, so if you are just, you have an architecture which is just doing and then just sitting for rest of the 495 cycles, it's a very bad design. It means that you have not, now you are using a lot of hardware resources to do it very quickly, and then you are just sitting there doing nothing. So your process utilization जो है वो सारी खराब हो गई है. So you got to, first of all, once you're doing a system level design, you got to find out the budget of every block, that how fast you want to run your block, knowing the target clock and knowing at what rate you are getting your data inside the process. Okay, the processor has to process these many samples, worst case, these many samples in a second, and it has so many cycles in a second, so how many cycles do I have to process? 500 means that there is a potential of folding the architecture 500 times. Whatever is running in Python, you can fold it 500 times, that architecture 500 times. Okay, so means if there is an adder, you can use that adder 500 times, the best case, because you have 500 cycles to do what is happening in your Python code, 500 cycles. So that is important, that without just jumping into an architecture, you must find out your budgets for every block, your system level architecture, your budget for every process that you have, so that you know that what is the best architecture that you can design, keeping in perspective these two numbers. The other one is more interesting, that your sampling is this, but you wanted to do gigabit per second. And now you have 500 megahertz clock cycle. If you divide it by 2 giga, it means that you got to do something 4 times better than your clock rate. Okay, so it means at least 4 time replication of the same architecture, so that you basically get in step with the data rate if you want to be real time. So you say, no, I want to do 4 times, sometimes it is 10 times, sometimes it is 100 times, and this is where you have to replicate what you are doing in the algorithm in a cycle so many times to get to this speed. So that is another challenge. So that is a challenge of how you basically parallelize the algorithm so that you can have multiple instances of that. And if it is working on the same stream of data, it even becomes more challenging. So if there are multiple streams, then you say, okay, I can always put one stream here, one stream here, one stream. But it is just one stream of data, and you got to figure this out in the stream. That is a very, very challenging problem from the architectural perspective. Let's say networks is just a packet you have to process, okay, and you want to do it 4 times the data rate. So what do you do? Okay, because first of all you need to figure out it is a packet boundary, and this is the end of the packet, and only then you do the further processing. All the DPI, deep packet inspection engines have this challenge to solve. Okay, so the best is, you say, I have a very simple use case. where my clock frequency is equal to the sampling frequency. The rate at which I'm getting the data, I process it, and so it's very easy case, and especially if you're doing sample by sample processing, it becomes very easier things to process, especially front end of all these receivers which are just doing noise cleansing, wideband noise separation, and so they do the sample by sample processing. Usually these are just filters that are cleaning the data at the wireline speeds, so at which you are sampling. So you are just cleaning and then passing it to the rest of the system. So there preferably, usually you are sampling at a very high frequency and your clock rate also matches with the sampling frequency. And you say, this is a very easy architecture to design because now you have this input data coming in. This is the previous sample, this is the previous to previous sample. These are the multiplication by a constant with the previous multiplication by a constant with the previous to previous multiplication by a constant, and then you are adding and adding and then generating the output. So and your every clock, this clock cycle and your analog to digital conversion clock cycle, they both are the same, running at the same clock rate. So every 500 megahertz you have a new sample, and every 500 megahertz this also register gets a clock, so it saves the value, do the processing and give you the output. So usually to design these architectures, you draw the algorithm as a DFG, data flow graph or signal flow graph. So you design, you have DFG or SFG, both are fine. So it's just laying out your algorithm on a paper that this is what the algorithm is supposed to do. This is precisely what I did once we were doing sorting out the list of numbers. So this is precisely what we did. So you need to sort out the numbers, and you say every clock cycle these are the numbers. So you say, okay, in a one clock cycle I will sort all of them out. But then you basically drew the algorithm and you open up all the loops. So what you do is you go to the Python and say unroll loop, unroll loop, unroll loop. So once you ask Python to unroll loop, it will just start unrolling the loop. So every for loop, just to see that how much amount of processing that you have to do. For example, you go to Python and say design. Here is, for example, I say generate so first thing is, let's say I ask generate Python code that implements a 3x3 kernel on an image of size 12 into 12. Okay, so it will generate your Python code. So this is a very basic operation in all convolutional neural network, where you have a kernel, and many of these kernels are just doing this type of processing, and it has used just the convol function. Okay, so now you say that you don't want it to use, say, instead of using the convol function, use Python code to do the convolution. Okay, now you ask it to, so hopefully it will now, so it has now these loops. Okay, so as you can see, this is the amount of computation, image height, image width, and then it has all the multiplications and additions that are happening, and then you can, I don't know, it may get angry on me, but I can still ask it to unroll all the loops in the code to see all the computations happening while applying the kernel on this window. It has not actually ये वो कर रहा है. This is kind of the unrolling region, this, and so apparently you can just see that this is the original image, then the kernel, then all the multiplications that are happening through the kernel 1, kernel 1, kernel. So should have done it with. So you can just open up the loops to see the amount of computation happening, and or you can just draw it yourself. Okay. So here is an application where if you want to, for example, develop, this is an interesting application where you have a CD quality audio which is sampled at 44.1 kilohertz, and you want to record it on a digital audio tape that records a signal at 48 kilohertz. So it's a sampling rate changer which takes your 44.1 divided by 48.0. So it is actually 441 over 480 sampling rate changer. Though seems like a very simple architecture, but very complex actually to design, because you have to first upsample it by 441 times, and then you have to downsample it by 448 times. So it's kind of, though it's just you are taking a CD quality audio onto a DAT tape, and you cannot do just directly put it on a DAT tape because you got to match the two sampling rates. So here is the architecture, which is has divided. We will not get into the detail from the signal processing perspective, but it says you have the CD quality audio coming in, and you got to first interpolate. For every sample you generate 2 samples, so you got to upsample it. Then you have to collect 3 samples here, and once you have 3 samples you will convert them into 4 samples, so 3 by 4 converter, and then you need to have 7 samples and you will generate 5 samples. Then, so if you multiply 1 into 3 into 7 into 7 into 1, and you multiply 2 into 4 into 5 into 4, it will give you a ratio something like this. So what you are getting here. So now and this is the architecture that you are going to design. So this is a block, this is a block, this is a block, this is a block. Every sample it fires, it generates 2, but this cannot fire because this requires 3 samples. So you fire it once, and then you fire it again, you get 4 samples. Once you get 4 samples, you use 3, left is 1. And next time you get 1 sample, so you have 2. So you get 2 new samples. You already have 1, so you get 3. So you can fire again. So you are not firing, then you are firing, and then you are firing, and then you are not firing. So once you look at this, and if you are at system level, you are designing such an architecture, so you will realize that it is quite complex. If you just use that approach where you say, okay, whenever I have enough samples, I'll just do and execute. Okay, and sometimes you have more time, sometimes you have less time. So you have to design according to the less time, because you got to make sure that you may be firing twice. So the other one is that you find out a firing sequence, and this is the firing sequence that you first 147 times, and this would be fired 98 times. So 100, you collect 147 samples. I think this is A. You run it 147 times and collect all the samples at the output. Then you will able to fire this 98 times, okay, and collect all the sample at the output. Then you will able to fire C 56 times, collect all the samples at the output, and then you will able to fire. Now this is kind of a fixed budget. It requires some memory at the input of every block, but this is a cyclostatic schedule that every time now you are collecting. Let's wait for the azan. Okay, so it's like, so you are going to fire, once you fire A 147 times, how much memory you need at the input and how much memory you need at the output. Obviously at the input you need 147 memory location, and at the output you need 147 into 2. So this is the amount of memory you need. And then you are going to fire B 98 times and generating 4 samples every time you generate this. So you need this much memory. Then you are going to fire C 7 times, generating going to 5 samples. So you have these men. So means, and then finally you are going to execute this 40 times. But everything will be working in parallel now. Yeah? So this is generating 147 samples. This will be generating 198, 147 into 4 samples. This. So everything will be working, and you know the exact budget now. That how many cycles do you have? You have 147 cycles to do all of this processing. You know? So that is something where you can make this thing more interesting, putting a little bit more memory. The other one is the down, where you say, no, whenever I have sample, I'll make it fast, and whenever I have enough sample, I'll go and execute. Okay. For that case, so this is the second case where to fire as soon as it gets enough samples, and so you need very little buffer. So here you only need to save one sample. One sample comes and you say, okay, you go start. Here maximum you need 4 samples, because 3, so you may have 2, 4 samples, then you give 3. So you never require more than 4 samples to be stored. So similarly, as you are moving on this line, you require less memory, but the architecture becomes little trickier to design, because it will be working, then not working, working and not working, will not be fully utilized. So one way of looking at the algorithms are that you have data flow graphs, and there is one node which is connected to another node, which is connected to another node, and so you draw your algorithm like this, like I have drawn it here, this way, okay? And then you may have, and especially, usually you will have cyclostatic schedule. That schedule will start repeating itself after a while. So, and you draw it like this, that once it fires, it generates 2 tokens, and how many tokens it consumes, and generates how many tokens, so that you have a representation of the algorithm in terms of a data flow graph. And from the data flow graph, you try to design an architecture. Wherever you see a dot here, it means it is storing a value. So this node will be requiring the previous value. So it's a register, physical register, okay? If you don't see this, the same value goes here. But if I put a dot here, it means it is not this value which it has generated, rather it is the previous value which was generated. Like in the filtering process, we have something like this. So this has current value, and this has previous value, this has previous to previous value, this has previous to previous to previous value. So a dot means previous value. If there is no dot and it is just one line, it means it is using the same value. All of them are using the same value, and it is just getting multiplied. And so this is, for example, this is a storage and a storage, but then this is using the same value. So this all has to happen in the same cycle. Okay, these two, multiplication and addition, got to happen in the same cycle. But here you are storing a value. Storing a value means here it is using the previous value, which is previous output, and here you are using previous to previous output sample to have the diagram completed. So let's not worry. So here is you try to figure out, this is the cyclostatic schedule where you say you fire A once and generate 2 tokens, and these are the previous values, and then you fire B, it requires 2 tokens, generate 1 token, it fires C requires 3 tokens and you generate 3 tokens, and once you have generated 3 tokens, then A has to consume those 3 in 3 firings because it requires only 1 at the input. So it does A, then A, then A, but it is executing in 1 cycle, whereas B is executing in 2 cycles. So B and then small b. So you fire A, you fire B, then you again fire A, but the second part of the B. Then you fire B, because you cannot fire C unless you have 3 cycles. So you fire B, then you fire A. A you are firing in every, after this every A, after 1 A, and then you have B, B. Then now you have 3 samples at the input of C. So you have to fire A 3 times and B 3 times to generate 3 samples for C to fire once. Okay, and C takes 2 cycles. So these 2 cycles, and now there is a cyclostatic schedule which you can follow to run this algorithm. Initialization, and then you say now I am going to do this. So you fire C, C, then A, then B, 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 and then again C, C, C. So it's in this fashion, you just keep on repeating itself if you have like such an architecture. If you don't, then it is simple. You have operations in the flow graph, and for every operation you put a hardware operator, and that's how you. But if you think now you are not meeting timing because now the cloud is much bigger. So let's say it is addition, it is addition, it is addition, it is multiplication, and this path is taking too much time, and you cannot run your circuit at 500 megahertz. Rather, you are only running it at, let's say, 200 megahertz. So the only way to make it faster is either you use faster building blocks or you insert registers in between. So these are the registers, and if it's all feed forward computation, registers will only add latency. Now you will get a result after so many clock cycles or in the same clock cycle, but you will able to clock the circuit faster. So the one-to-one mapping implementation is very simple. Take the algorithm. I remember the hashing algorithm where we had a comparator, a comparator, a comparator, a comparator, then we were doing this comparator, then we were doing this comparator, something like this comparator, and then again we were doing something like this. So it's comparator, comparator, comparator. So there was a path which was taking so many comparators. And you say, oh, I can only run it at 50 megahertz, where my target is 500 megahertz. So what you have to do is put registers in all the path, all the path, all the path. The only bad thing about the registers is that if you are trying to make your critical path faster, you have to find out all the paths that are running parallel to the critical path. So you have to cut the circuit vertically and put registers everywhere so that they are synchronized, that every clock it is getting new data, and the new data, and after every 5 clock cycle it gets the result of the first sorting, then after that every clock it is getting result of sorting. So the dedicated implementation would require you to draw the algorithm and then put it the hardware building blocks, and if there is a previous value, so you need to put a register. This is called an algorithmic register. This is not a pipeline register. Okay, so there are 2 types of registers. One is part of the algorithm, it is using previous value. So wherever your algorithm is using a previous value, it is the algorithmic register. Wherever you are making your circuit faster, it is a pipeline register which has a very different dynamics. Usually these are very valuable registers which are algorithmic register because they are already there. They are already breaking your critical path or your cloud into parts. So these registers are very valuable registers. Okay, So if you remember, we develop a linear predictor by saying, let's say stock market, and I'm developing the hardware for a linear predictor. So I have all these stock values, the current stock value and the previous stock value and the previous stock value, and I have a window of n, and I have these predictor coefficients. It's a linear predictor, so I'm just multiplying all these. So every predictor will be something like this. Every predictor, it will have a window, and it is a timestamp data. Whether it is you are predicting the population, you are predicting the price of gold, you are predicting the price of a Bitcoin, anything that you are predicting. So it requires a time series data. And if you're doing it real time, usually once you are doing stock market, if you're doing high frequency trading, and you have, imagine like 10,000 stock values getting into your predictors, and your predictor is just predicting, and then they're sorting, and then they're figuring out that where you can get maximum gain, then they are suggesting. It's all in hardware on wireline speed. So you're just sitting on the network which is getting all the values of the stock market indices, and your predictor is kind of predicting and telling people that this is the best stock to buy, because, or it is automatically buying and selling stock because you have allowed it to do that. So, but these registers, if you look one register to another, to another, to another, to another, to another, is not adding any value, so to say, for breaking your combinational cloud into pieces, because you have a big combinational cloud, which is this one. It has to do the multiplication, then addition, then addition, then addition, then addition, then addition, and finally predicted output. So this path becomes a critical path. One multiplication and so many additions. And after that, you can take a new value. If you take it before that, you are going to get wrong answers. So you got to make your circuit fast enough. Let's say this length of this is 5,000 previous values, and you're doing it on wireline, 5,000 previous values of the stock that you are using to predict a new value. So 5,000 adders delay will be very, very slow. Why? Because, and you are not using these registers to break your critical path somehow. So sometimes these registers are valuable which you can move inside your circuit. Systematically you can move all your algorithmic register. This is very interesting. All your algorithmic register can be moved inside your circuit. And movement is interesting. Why? Because if there is a register and there are now 10 paths. So once you move it from this node forward, so you are going to get a copy of the register on every path, because an algorithmic register, it was just delaying this sample which is being fed to 10 different branches. So now you get 10 registers, which are algorithmic registers again. You are not adding any latency. So algorithmic registers are sometimes very, very valuable registers, and we will see that the value of these registers, that how you can best utilize it. But one-to-one mapping is simply that you see all the computation that you have to do. Okay, for example, this is your algorithm, just a hypothetical algorithm. You see, wow, I have to do these many multiplications and then additions, then again multiplication, addition, this, and then I will get a final answer. Whatever algorithm, I'm not concerned about any algorithm that you are doing. You say, oh, and this is, and especially if we go and find out the algorithm for this, yeah. Here is hash. Yeah. So if you see, these are all the cloud. So all of this you have to do in a single cycle. These are simple ANDing, ORing, but there's lot many addition. H plus S1 plus CH plus K plus W. So this is my combinational cloud. So all these additions are my combinational cloud, that I have to add this plus this plus this plus this. So all this is going to be in my combinational cloud. So all these additions. So I have H plus S1, then I have CH, then I have K, then I have W. So I can find some interesting way to add this, but this is my combinational cloud, so doing all of this addition. So this would definitely is going to determine that how fast can I clock my SHA-256 algorithm, and what all I can do, because it's also feedback, because this iteration will fed into the registers again. So once you have a feedback algorithm, then it is even challenging to add pipeline. We cannot just add register, because if you add register, you will delay the computation. It is expecting the next iteration is expecting computation coming out of this iteration. Okay, so you start getting things that, okay, now though I have a dedicated parallel architecture, but what should I do to reduce the critical path of all these additions which are happening, and then it is fed to another one, then another one. So these are the type of things that would definitely requires you thinking that one-to-one mapping is good, but in one-to-one mapping sometimes you will not be meeting the critical path. Okay, so first thing that you can always try is that you have different type of adders, different type of multipliers, different type of shifters. So you have different type of units, and there's a trade-off. Like you spend more area and you can make them faster. More area and you can make them faster. So usually it is something relationship like this. Okay, so if this is the frequency, clock frequency, and this is area, so you put more area, you can clock it faster. Okay, and there are so many options for simple adder, that one is the simplest adder, which is a ripple carry adder, which takes very little area but very slow. And then is a conditional sum adder, which takes a lot of area but it's very fast. So you can first explore in your RTL design all the options of different adders. Okay, let me use this one, and this multiply this adder, this multiply this adder, and see that how good a result that you get. And then there are some resources on FPGA. The problem with FPGA is that usually you have to be very cautious once you are using these resources, because these, for example, these are different types of FPGA, Xilinx FPGA, which has 600 DSP slices, these many. And your algorithm, once you look at them, they require hundreds and thousands of multiplication and addition. So it's not possible that you put everything on, let's just consume everything. Here is your budget, and this is very hard deadline, that you cannot just consume all of them. So you got to be cautiously consuming. Usually once you are implementing something, it is something which is very a serious implementation. You see how many resources I have and how many can I use. If you run out of these and you are continuously adding more and more functionality, then it will be difficult. And I have seen usually people initially they don't care, and they design something which does not require so many adders and multipliers. Consume everything, and then nothing is left for others to actually use. The other people, if there are multiple people working on the same FPGA. So got to be cautious about what all you have. So you have all these DSP processors, but then you have only limited supply of these. So you need to decide how cautiously you got to use these multipliers and adders. ये जो इसके अंदर रजिस्टर है ना, if there is for example जैसे ये रजिस्टर है, it will check whether you are registering the output of an adder or not. If you are not, it will pass it through this mux and make it go straight to the output. But if it finds out नहीं आपने तो उसको clock कर दिया, so then it will pass it through a register. Okay, so you may not be using the register because the way that you have written your code, you are not using any register at the output of this. So it depends. So if you see there is a parallel path, there is a path which is going through 2 register, there is a path which is going through 1 register. So there are 3 paths. Okay, but this is a resource. So all these registers are resources. So it will check whether before you multiply, are you using a direct path or you're using one register or you're using two register. It will accordingly map your RTL Verilog code to this design. Okay? So, but that's why this is an FPGA, because it gives you all perceivable options to use a multiplier and an adder. A MAC. So it says, oh, you are using a MAC. So a MAC means that somehow you need to take your multiplication result and feed it directly to the adder. There is a way. Okay. So because now MAC is multiply accumulation, so it'll go and, but obviously once you look at the clock rate, you may not able to clock it at a very faster rate, because now there is a direct going to a multiplier, then going to an adder, then it is going out. So that's why the movement of algorithmic register to break the path to utilize these registers will definitely make it run faster. Otherwise, one block, it will connect it to the another block without having any register in between. So you have multiple of these and they are not using any registers because your algorithm is not using any register, because your code is not using any register. So you will not able to clock it at a faster rate. So for example, here is a code where you are saying, yes, use, sometimes you say, use DSP48, okay? And you say, no, don't use it. I want you to use my implementation of multiplier on adder, okay? And you say, use DSP. So wherever there is an addition, put DSP48. Where there is a multiplication, you say use it. So, so you are just adding three numbers which are input, and then you have, this is a typical MAC operation, but A into B plus C, and then your this product, and then you are adding D plus C. So you are doing some computation. For example, here is another example. If you look at this example, there is a big combinational path. So you are doing, here, this multiplication, this addition, this addition. Okay, so you have to do multiplication, addition, addition. So there are three blocks that, because multiplication, addition, it may try to put a MAC there, right? But then there is another addition here. And then it needs to figure out, and then there is another path which is apparently this one. Here again you have a multiplication and two addition, and this is also a path, and this is also a path where now you have a two multiplication. Okay? So you have a lot of critical paths in this design, and in fact, yeah, it is. So this is, once you code it and put it, just write simple code, and you can generate this code as well. But these are the constants, and a simple equation is like this. So you have a multiplication equation, reset. You are making registers equal to 0, but then you are assigning them to whatever that you have computed. So it's a simple to write code. And this is what the synthesis tool has generated based on your code, that how many multiplier, adder, okay, register. Okay, so sometimes you can just go find out the circuit diagram and see that how many resources are used, and sometimes you don't care. But here is the critical path. It says your sampling frequency could only be 91.59 megahertz, and now somebody has asked you, I want to run it at 200 megahertz. Okay, so now you need to worry about that. How can you break the critical path to get to this result, that you run it at 200 megahertz? Okay, so this is where then you have to see that how either you can use the algorithmic register, move them across the nodes to see if they can, because here they are not adding any value to the design, because there is one register and there is two registers. It's not breaking anything. Okay? It's just register and a register. It's not breaking anything. So it's not really helping you to break the critical path. Critical path is totally kind of separate than the registers adding any value. So that's why you need to find out how to. So this is on now. Once you map it on vertex 4, so it is now using MAC, a MAC. Okay, So it's using 2 MAC and 3 MAC and 4 MAC and a multiplier. So we'll just try to, but still it may improve your clock rate as well. So saying this means that whenever you have an algorithm, for example, this is a typical convolutional neural network, CNN, and we know, I hope that many of us know how a convolutional neural network works. For example, this is an X-ray, and it is going to figure out whether it has there is no problem or there is some problem, just simple 0 or 1, 2 classification. And now it is going through a number of stages. In first stage, you create through 32 kernels, you create 32 images. In another, then you create, so you are doing it downsampling by, it's 256 by 256. So kind of you are throwing away kind of every other sample, and you have 32. Then again you have another 32 kernels to produce 120. Again you drop every other sample or do max pooling, and you have 64 into 64. And this again you take the 64 into 64 and half it, and this is where you are 16, 16, 8, 8. You then flatten it, and then you pass it through a feature extraction. And now there is a company which says, I want you to do this circuit onto an FPGA chip, and where they are just feeding in X-ray after X-ray after X-ray. And they ask you that how fast, how many X-rays can you process in a minute or in a second, right? Because now you put it on a cloud and you are providing this service that you have designed a system which is cloud-based though, but you can just almost in real time you can process classify an X-ray using this specific model, and you want to design a hardware architecture to do this. And if you say I want to do everything in parallel, okay, everything in parallel, this X-ray should come and just get out of this whole thing. So now you need to figure out that how many multipliers, how many adders, how many registers you will be requiring, because registers you can just know that 32 into 32 into 30. So this is 256 into 256 into 32. Storage elements are to be there so that you can store them. Then these many elements, then these many elements, then these. So you can kind of roughly figure out the budget for fully parallel implementation, dedicated fully parallel implementation. Can you do it 200%? You can do it. Okay, 200% you can design a fully parallel architecture, which is the easiest architecture to design, right? But it may require a lot of resources. And you say, why should I care? I can have, I can have a 1 trillion transistor on a chip because I am designing it. So never ever worried about, usually hardware is always available, okay? Usually, okay? So usually there is no constraint on the amount of resources that are there for you to implement a design. It's up to you that what you are trying to design. If you're trying to design a CNN, okay, which could do almost near real-time processing and processing hundreds and thousands of these X-rays, yes, you can do that. But then you say, no, I only want to process one X-ray in 1 minute, for example, or 1 minute is good enough. And then you say 1 minute is equal to 500 megahertz and how many clocks you have in 1 minute. So that will be your budget. You say, oh, I have 1 billion clock cycles or so many billion clock cycles to do this CNN. So then there will be a very different approach. So you must not try to do this everything in parallel where you are only giving one X-ray per minute. Okay, it doesn't make any sense because you do process it and then you're just waiting after processing it in few millisecond or microsecond. Right? So the most important thing is your budget, that how fast you want to process your data. So sampling, FS, and then the clock that you are targeting. So these are the two most important aspects to see how much folding that you can do in your algorithm. How much should you fold? And obviously the fun is that you do everything in parallel so that you design something which is so fast. So then you got to understand the architecture that, okay, this kernel, a very simple CNN is very simple. It's just doing a kernel and you put it on an image and then you are just moving it. And now let's say I want this to happen for an image, all of this to happen in parallel. Okay? An image in a cycle, I have another image. So I get an image, in the next cycle I have another image, which goes through this kernel. So all these operations which you are saying happening in a single cycle. Can we do? Yes, we can do it. It's very simple. No issue. I have all these registers and I just figure out, unroll all the loops. Okay? It's just unrolling all the loops and give it to Verilog. How many multiplications are you going to require? You can figure this out. For every step, you need 9 multiplication, 8 addition. And then every time it is moving, 9 multiplication, 8 addition, 9 multiplication, 8 addition, 9 multiplication, 8 addition. 9 multiplication into 8 addition for every time it is on a pixel. So how many pixels are there? 1, 2, 3, 4, 5, 525 into 25. So 9 plus 9 multiplication into 25. Those many multipliers only for one kernel. Then you say there are 32 kernels in a layer. So into 32. And 10 of these layers into 10. Okay? So you can say, okay, I need only these many multipliers. Maybe you say I need 10,000 multipliers to do this in parallel. But you can very easily write up the front. You can figure out the budget that you have. You say, okay, I have so many adders, multipliers. And usually if you have this type of an application, you will have this type of a budget as well. Right? But design will be very simple. Design will be simple, though it looks like, but it will be very simple because whatever you see, you implement it. And once you say, no, fold it, then it becomes trickier and complex. Okay? So this is where the max pooling also happen in parallel. So it's like things are happening parallel. So you do this, then the max pooling, then you do this, then you do this. So, and then definitely every stage you are storing in a series of registers, in registers. So this is again a very simple operation. You can perform this. Then a fully connected layer can be a fully connected layer also. Okay? So all these nodes like 120 into 84. Okay, so these many multipliers and -1 adders. So yes, you can have a fully connected layer as well to do this in hardware. So CNN is an interesting applications because mostly in all image processing, CNNs are used. And the good thing is all their anybody who is coming with a new architecture, you get it, the model, they usually publish the model and the architecture. So you can get the architecture. This is an interesting application, which perhaps is the very first application of CNN, where they used these handwritten letters. In America, they used it for zip code. So they wanted the zip code to be read by a machine so that it sorts the machines out. So faster is better, as fast as possible is better. So they created an architecture like this, almost similar to what I have done. And this is the code which I have generated using ChatGPT. And it's almost 100% accurate. And this is the database, MNIST database. Actually, last night I was just trying to generate it and check how good the code it generates. But as you can see, it is first is it takes 28 by 28 image, and then it has 5 by 5 kernel, and then it do the max pooling, reduce it into half, then again use 5 by 5 kernel, 8 by 8, then again reduce it into half, 4 by 4, and then flatten it, and then it has another fully connected layer, have this, then have another fully connected layer, and then can do the classification 0, 1, 2 to 9. Okay, so this can be done everything in parallel. Like it's just so because so many letters that are coming in, and they have first every character they just separate it and they pass it to the architecture and just cranking and just figuring out what it is. And so this is where I actually generated these are the labels and these are the labels. And I think this is pretty much I should cover today. And in the next class we go to the timeshed design. and that how you once you have, so then you have so many options. Once it is timeshare design, then you have an option to, interestingly, a bit serial architecture is where you process bit by bit. So every bit, so all your data path is just 1 bit wide. So bits are coming in and getting processed. Word serial is you say no 4 bits together. Sequential architecture is, that was like your instruction set, sequential unfolding. Systolic is where you have some way of bringing data back into the architecture. Folded is that you fold the architecture if they are like 10 multipliers. So you have, if there are 10 multipliers and you only want to use 2 multipliers, then you fold an architecture in a manner that you use these 2 5 times. But then it becomes complex because you need a controller. Now you go and get multiplied, now you go and get multiplied, now you go and get multiplied. So we'll do this, and the last one is the microprogrammed architecture. So we'll see that how you do the microprogrammed architecture. So we'll just cover all of these architectures and see that how these can be designed. जो हमारा final exam, जो midterm exam है, next week we will have our midterm exam. Okay. And so usually what I'll give you is something which you generate in Python and then convert it into Verilog code. सही? और कुछ मैं आपको सैम्पल प्रॉब्लम दे दूंगा टू वर्क ऑन. कोई क्वेश्चन हो तो आप पूछ सकते हैं किसी. चैट सारा ये होगा, ओपन बुक, ओपन नोट्स, ओपन इंटरनेट. सो बस पास नहीं करने अपना कोड किसी को कि ये वाला इस्तेमाल कर लो. नहीं, हमारा नेक्स्ट वीक होगा एग्जाम. नेक्स्ट वीक इज गोइंग टू बी द एग्जाम. सही है? फर्क नहीं पड़ता, आ जाओगे तो अच्छी बात है.